Hello, welcome. Welcome to my Empire of Dirt. This is the fourth Dram hardware stream. It's just going to be me today. And yes, I'm getting started a little bit late because of AV issues and unpacking all the usual things there. First time I've done one of these by myself. So if you're in the chat, if you'd like to comment, please do. I'll try and keep an eye up here. I think part of the reason I was just so late is because I was starting a second monitor, and I have that now. Otherwise, I'm going to be kind of heads down, looking at layout. So the things we're going to do today, well, let's do a little recap, actually. I also need to pull up some supporting material. All right, let's do that. Today, we're in the fourth session of the Dram module. As a little bit of background, this is a 24 by 34 millimeter castellated edge module. And castellated edge just means basically when you sit the kind of a board on top of another board, and then the solder flows up the side of these pads because they're plated. And so I think we did that in session. I think we actually did that in last session. I will be honest, I got a little carried away, and I've made some changes since then, and I will go over those now. But some of the things we're going to do today is hopefully route some pins together. I kind of said that we were going to do that in the first video, and that did not happen because we were almost figuring things out at that point. So I relabeled some of those videos, the older videos as well. So like I said, this is the fourth in the series, and yeah, we're hopefully at the point where we're actually laying some tracks down today. Let's take a look at the schematic and where we are there. The schematic is not 100% yet, so this is going to be kind of still roughing it in, but I think the important stuff will be done today. And one of those things is in controlled impedance traces. And if you don't know what that is, basically it's a controlled impedance is like saying something is like 50 ohms. So if you're trying to connect to an antenna, or say you've got differential pair like D plus D minus on USB, or a range of Ethernet has differential pair as well. But the idea being that you have a characteristic impedance the entire length of that trace, and in doing so, you can have good signal integrity. So that's what we're really going for with that. This board, this module that we're making, has 3 RF feed lines on it. So going out to U.FL connectors, those are in the corners, and then 1 spare that we just won't hook up. And so that's going to be some of the stuff we show here today, that controlled impedance line there. There's lots of many better videos there. I'm going to basically just be following guidelines based on the PCB manufacturer that I'm going to use, which is going to be JLC. And if you don't have other specific needs around your stack up, which I don't really, I just need to have it to be 50 ohms. There's not a ton of value in going completely custom stack up because it might add costs and whatever. So instead, I'm going to go target some of the existing stack ups and then use some of their capabilities, some of their resources that help me to figure out what my trace width should be and my spacing from the ground planes in order to capture the same kind of thing. Okay, lots of talking here today, and it's just going to be me. I also, my microphone's plugged in because you may also notice that it's, well, it wasn't charged when I got started, so I'm a wired microphone until it's charged up, but it's a USB-C, so hopefully we'll be good there. Hopefully I don't feel too awkward taking a couple sips of soda there. All right, so let's look at the schematic first. Like I said, this has advanced quite a bit. It's almost like that, if you've ever seen that like Reddit meme about like draw the owl, like from it's showing like 2 circles, and then there's a little bit more sketch marks, and then finally it's like this fully done owl. And I'm trying not to do that. I'm trying to explain the in-between steps here, but we'll see how that goes. All right, so I have to share screen. First time ever doing a live stream by myself. That's surprising. Well, maybe not the first time. First time for Goliath. Okay, so this is the Dram module. This is the Dram 1 module. I guess I could zoom out a little bit here. We actually have 4 modules and a bunch of other things on the in the project as well. Sloshy McWashy is our Friday live stream where we're building an IoT device. we're actually going to be using the Dram module on that as of right now. I also build out like a circle Dram, micro Dram, and then Dram on the Goliath. All of these are just kind of places that you would land a Dram module, right? And so we needed to have a footprint that would match the module card edge that we're making here. We take a look at what that looks like. So let's actually look at the circle Dram. So this is the circle Dram. It's got USB, it's got some buttons, it's got buttons on the bottom side, programming headers. In fact, we can go here. I even exported the 3D models from the Dram and then show it. Now, it doesn't show the cutoff on the edge here in the 3D model, but it does show it on the 3D model here. So yeah, the STL didn't do it, but so that's what the circle Dram looks like. On the back side, there's just a big, just a big battery holder. So, and this is really what drove a lot of this specifications around this, but it was super easy to make this circle Dram board. Same with micro Dram. Basically, there's kind of a standard set of components you would have around the edge of your board, or sorry, surrounding your module. Micro Dram being one of the smallest versions of this thing that we can make. The circle Dram, I guess, is a little bit smaller, but it has more functionality. And yeah, I think I wanted to have some examples of this stuff so that we can actually show it in situ and then see if there's any other requirements that pop out of this sort of thing. This was one, Dram on the Goliath is just showing it on the Goliath. This actually needs to be reworked a little bit because it's there wouldn't be enough edge. You have to make it a little bit wider than the footprint of the Dram module for the board itself. So that is not quite there yet. But you see that there are 4 different Drams so far. Got a little carried away. But what this helps show is the fact that this is an abstraction layer, basically. So we're defining this outer footprint here, right? These castellated edges. That's basically when you have like a through hole and you cut it in half. It's a special process that board houses will do for you. It'll add a little bit of cost. But once you have that and you have the pinouts, then you can start to put different parts on there. And really that's where my interest comes in because, oopsies, sorry about that. That's where my interest comes in because using things like Zephyr or ESP-IDF, you can actually start to target the same functionality, the same, so if you land this module and say you have the circle Dram and you have a sensor, like a accelerometer hooked up to pins 26 and 27, and they're always hooked up to pin 26 and 27, it actually doesn't matter what's on the inside of the Dram as long as it knows that those are SDA and SCL, the 2 I2C pins, right? And that means that we start to we can take advantage of a lot of the abstraction that exists in the RTOS layer as well. So you could have modules that get called there, and then you can also do things like targeting different regions. So if you don't know, a lot of cell modules are region specific, and you can actually get a lower cost one that's not a non-global one. So you could actually have a lower BOM cost by having one that targets North America, and one that targets Asia Pacific region, APAC, one that targets EU region. And you can lower your BOM costs by building in your own modularity in that way. And modularity is a disease, and I do have it. And we try not to overdo it. So, and I've been down a couple rabbit holes so far. But ultimately, this is what we landed on. And so, Dram 1 is NRF 9151, which is the cellular plus GPS module that's in charge, just the main processor on there, and then ESP32C3 offload to do Wi-Fi locationing, and then Bluetooth if we ever enable that. Does not currently have that. That's hooked together over serial. On this one, this is the NRF 52840 Bluetooth chip. Very easily could be a 5340, the new 54H20, 54L20. Those are all different processors that are available there. I should note that 2, 3, and 4 are not as hashed out as number 1 is here. That's what I've been focusing on 1 when I've been doing, adding 3D models, adding schematic symbols, things like that. So a lot of the stuff from once 1 is done, that'll kind of flow its way through to 2, 3, 4. But the key thing is that the footprint is the same, right? The footprint of the module is the same, and the functionality is the same. And then we make sure we hook up the pins so that I think on the left side here, pins 11 and 12 on the module, I'm sure like over here, making sure that those are always hooked up to analog enabled pins on whatever the main processor is. So in this one, it's nRF52840, and then this is a BG77 cellular module here. The form factor, the BG7X form factor, has other parts in it and could potentially target other ones in the future. But really, the idea being that once you have AT command sets in here, if you're using something like Zephyr on the nRF52840 and the modem library, that kind of abstracts a lot of the capabilities and functions and kind of the things that are making the modem connect to the internet, give you an internet connection. And then it's just kind of a connection to Goliath. So my goal with all of these Dram 1, 2, 3, 4, to infinity is it's a Goliath enabled module that ultimately has different capabilities in terms of connectivity, in terms of regions, in terms of low power, things like that. But ultimately, that they are all drop-in replacements for one another, and that's where it gets kind of difficult. Specifically on Dram 3, which is the ESP32C3, which requires a GPIO expander, which is not on there yet, but it will be in the future. That's really the most stringent use case, and that came from the Sloshy McWashy project. Can we get a low-cost part that's now in charge, right? The ESP32C3 being in charge, low cost, doesn't have a lot of requirements, and then still make it all work together and cover all the pins that we need to have. Because if I say I start with the Dram 1 on, so I take the Circle Dram, right? This is my product, quote unquote. It's like Sloshy McWashy. I start with the Dram 1, and then I want to cost down later because perhaps the Dram 3 is lower cost or has different capabilities I need. I would love to be able to just drop it in there, and as long as the things are hooked up properly, the pins are all configured properly, it should be a firmware switch, really, not a reconfiguration of any other of the base hardware. And so, like, even to the point of having one Circle Dram main product idea, so Sloshy McWashy being in the same format as Circle Dram, being able to literally have a version with Dram 1, 2, 3, or 4 on it, and it has this exact same functionality. That is the goal. We are a ways away from there, and I am a ways away from doing fast videos. So I keep explaining myself over and over again, but there are 3 other videos you can go and watch, and lots of wringing of hands and back and forth of whether I should do certain things. Things I have figured out since then. Let's go to the Dram schematic. That's Circle Dram. That's the fastest way to do this. So if I click on the part on the Dram 1, there we go, there's a C3. Okay, so that takes me to the part on the schematic. Nice and big letters up here because I've already made mistakes where I think I'm on the wrong page than I am. So that's why I like these big, very obvious things. This is Dram 1. And Dram is some very ancient version of, probably in your head you're saying Drachm. I'm saying Drachm too. So, all right. So this is the footprint I created for the actual card edge, right? That's what we did in the last video, in video 3. We actually created pin associations. I actually made it so that this kind of looks like the pins, the edges, because I thought it'd be confusing otherwise. And this has actually been very useful for my personal style, so that I know that, like, oh, when I hook up DP and DN, right, that's going to be at the top side of the module. That's fine. Then I went and assigned. So a lot of this stuff came from our open source IEDL Elixir board, which is like a big version of this. And my goal, my longer term goal, is to make it so that the Elixir board that we can make another version of the Elixir board where we drop the Dram module onto it. That is ultimately the goal there, because then that would be like the most proof positive that we can make this work. And the thing that'd be cool in the Dram 1 case is we have the NRF9160 on the IEDL Elixir. This is using the NRF9151, which is actually yet to be released, but we can have access to the footprint and some of the recommendations and some of the application notes that we got as partners. And once we have that, if we could drop that on the Elixir, we actually get like a 20 dB boost. We get smaller parts here. We would save a ton of real estate on the Elixir board, which we have a lot of. And we would then be able to use that as a side-by-side comparison, showing the Elixir Rev C and Elixir Rev D, which would be using the module version. We would then be able to prove stuff out in this kind of bigger form factor with microbus click headers, clipboards plugged in to the click headers, and then we could say, yes, it works, all the reference designs work, and now you could take that exact same functionality, rip the module off, put it on a board by itself, like the circle Dram, put the one sensor you're using, say you're using just like a BME 280, you take that one sensor, put that on the circle Dram or whatever your product's called, and you're off to the races, right? So it's like the fastest version of going from like a prototype, bigger prototyping platform, which has these fun capabilities, take what you need from that, and especially the core here, which is the circle Dram, or sorry, the Dram module, take that off, put it on your board, away you go, right? And the idea being that you can then use the different versions of the Dram, that it should be a firmware switchover to make that work. Okay, so in doing so, I matched all of the pin numbers here to the to match the Elixir, right? So I started from the Elixir, so I wanted to match the pin numbers to have the Elixir here as well. And I think it's right. I'm going to be continually checking that sort of thing. But basically, that's kind of where that spreadsheet started. Let's see if I can pull that spreadsheet up. Spreadsheet up. There it is. And so really this Dram 1, this started from that, started from the Elixir board, and that's really where all this stuff came from. And so any changes that we've had has been since then. So yes, and 3 and 4 are still kind of being shook out as well. Really, I just wanted to get to the point where I was confident that we could make it work. All right. Even here, I've already I messed up some pin names here, but I haven't done that schematic yet. So really, I'm just focusing on this column, and potentially might even switch some of these, because as we'll see as we get to the layout, I started kind of like looking at the layout and what's called the rat's nest, which is showing where the connections are. So from pin P.00 of the 9151, that should be going to DG00S on the edge of the module. But if that has to go across another signal, and if it's just a generic GPIO, like it doesn't matter that much, and we can switch that. This is like a pin swap kind of scenario. So we can do that to make the layout easier. And it might be worthwhile because we're very much in like the nebulous, figuring it all out land right now. And once we, lock this down, I guess even afterwards, like you could have another Dram version that has a different pin assignment as well, because it's all done in Zephyr, and because you have board files that would represent, the pin muxing that happens internal to the chip itself as well. It should be pretty easy to swap them around. So we'll try that out as well. Okay, lots of talking from me. Other things that are different, what did I show in the last one? I ripped some stuff off of here. Yes, that is a big one. So I took the MFF2 off of the board. It was just too big, and it didn't really make all that much sense. And so let's go to the 3D model again. So on the micro Dram, right? So this is basically taking the Dram module on the backside and then having it plug into a micro bus click header. Right. That's basically one of the smallest versions of this that I could think of. I could put the MFF2, so basically an eSIM to talk to the cellular module on here, but the size didn't really make all that much sense. A lot of the newer parts have what's called an iSIM, so that's where your SIM information gets programmed directly into the module itself. And so I didn't really see a lot of value in that. Instead, I did assign, I think, these 4 pins up here to the SIM so that you could bring it off the module itself. If you wanted to, you could bring it off the module and then bring it to something like this micro, what do they call it? Micro SIM form factor. And so it could be like that, or on the circle Dram that actually would not fit one of these micro SIM form factors. So you couldn't have a replaceable SIM, but you could put an eSIM on the back of that thing. And that's something I've yet to do yet, but I think that actually makes sense. Or you could just leave it off and just program the iSIM directly into the NRF 9151 using something like Anomondo. So lots of options there, lots of optionality is what we're kind of designing in here. Whether or not that is necessary, there is no smaller form factor for eSIM, unfortunately. MFF2 is kind of the standard. I think after that they said, well, if you're going to go any smaller, you're going to put it into the module itself as an iSIM. So, and it was pretty sizable, almost to the size of this memory here. I took them all off, but Okay, so what is this other stuff then? So on this board, on the Dram 1, this is the 9151 that's in charge. This is the secure element. That thing's tiny. That is kind of a generic um, certificate storage part from Microchip. Um, Nordic people would probably say, well, why don't you use certificate storage on the NRF 9151? And that is correct. You do have certificate storage on Nordic parts. But because we're trying to have similar capabilities across all these modules, it's better to actually, in my mind, it's better to actually have a standardized way to do it off chip, even if it adds a little bit of cost, because, and it's cheap, because then you can have the same cert process across all these modules, right? Instead of saying like, oh, Dram 1 is our 9151 from Nordic, so we'll use that cert process for that, but then the Dram 2 needs a different cert process. I say get rid of that, put the footprint down, and then if you really get in the bind later on the Dram 1, you could always use the internal storage as well. Okay. What else happened here? Yes, the this flash. So this is external flash that is on a lot of what's on the Alliadel Elixir, our open source board. Basically, it's a 4 megabyte flash that is external to the part. And this is really, really useful for using Goliath OTA. So for example, when we use the NR52840, that's got a megabyte of internal flash. But when you want to do something like OpenThread on there, which we've done before, which is built into Zephyr and is awesome, you can't get that image smaller than 700 megabytes. So you can't do an A/B. So you need Delta updates, which we don't support currently. And so instead, you have to have an external flash. And Marco or FAE actually showed this. There's a video and a blog post about it. If someone else was on the stream with me, they would show it, but you have Google. And so Marco reconfigured the Goliath reference design template to work with Thread, to work with an external memory as well. He worked on the mapping. And so now OTA works flawlessly with OpenThread on the reference design template. And so that is just super cool. So being able to do A/B updates with a thread, with open thread network over IPv6 using 6LoWPAN, like I'm just saying so many words right now, 802.15.4. All these things work currently with our stuff because we have this external memory on it. However, this little guy here is big, a little too big for my liking. And so instead, especially when we start to use bigger BG77 modules, not that much bigger, but enough that like it really does start to matter because we want to have some additional room up here as well. You might be asking yourself, what is this bottom right UFL used for? The answer is nothing currently, but in my mind, the PhiPi, which was arguably expensive, arguably power hungry, and arguably like overly friendly MicroPython version of this kind of 5 radio thing. I loved it though. Like the fact that it had cellular, it had Wi-Fi, it had Bluetooth, it had LoRa, and it had Sigfox, and it had GPS. I guess I don't know if they counted that as a radio. It is a radio, but I'm not sure they counted it. But it had all those things because it had a sequence module, it had an ESP32, and it had the Semtech chip on it. So I think at some point in the future, I'd love to make a version of this that also has a Semtech like SX1276 on it. So then you also have ISM band radio available too, like 915 megahertz or 868, depending where you are, or 902 Australia, whatever. Okay. Drink. For all you people who are watching now, later, whenever, thank you for watching. And let's actually talk a little bit of layout now. Okay, so we talked a little bit about RF. These are all going to be 50 ohm traces for RF. That's just kind of the standard that I work to. I think some people do 75, but it's like way fancier than I ever would do. USB is 90 ohms differential. Ethernet, I believe, is 100 ohm differential. But we're just going to do the RF stuff right now. So let's talk a little bit about that in KiCad specifically. So let's look at where the connections are happening. This is under specified right now. I need to put a pi filter on here. I don't actually have one. I should probably just drop one in there. I have one on here. Wait, that's not, well, we're just going to copy paste this one. I know that is incorrect, but we're going to just copy paste it in here just to make sure I don't forget it later. What is that? That's to ground. Things to know about me and my RF. I once gave a talk called at Hackaday SuperCon called "An Analog Engineer Learns RF." I'm still learning, um, and I will add a note here. The reason I'm really doing this is because it shouldn't matter if you have if you have the footprints in there in a Pi configuration, you should be good. That is not going to work. What am I doing wrong there? That is wrong, wrong, wrong. Yeah, that is a weird configuration. Let's just do it like this. This is borrowed from Jared Wolf's wonderful NRF 9160 Feather board, which is certified. I do recommend it. That's also available as the Thing Plus from SparkFun Electronics. It is a very often used part in our arsenal. We're going to align the grid. There we go. There we go. Okay, it's all connected now. I'm just going to do a call out here. Values borrowed are wrong. Recalc or no pop. In fact, let's do that here as a matter of course. If you don't know, in KiCad 8, can I get it? Oh. My context windows are up here. So we're going to do not populate. I love that there are like big X's there. I think it's Control Alt X. Yeah, there we go. I really like doing that. So then this is basically only going to have a capacitor in line. That's fine. I just want to have that there just so I don't forget about it later. But the key call out here, actually that's going to break some things, is that I named this net. And so I did that so that I could then go in layout. You want to tell the KiCad layout program, PCB new, that this net specifically needs to be 50 ohms. And then from there, we can then go and use some of the calculators we'll look at in a second here. Okay, so I need to give this a different name. Feed. And then this will become clear later. That's why you also don't want it to be the same net name. So try and connect it. There we go. Okay, so now we have, and I know that this pull-up's going through here, but now we have a feed line going into this Pi filter, going out to the antenna, really the UFL connector. Some of the stuff still isn't hooked up and it shan't be here. I'm still checking some things. Let's hit F8 and we'll get these new components in here. There we go. Let's move this up a little bit. Hit B to redraw to your ground. There we go. These are showing the values, but they don't need to. Now you might be wondering, why is this called a Pi filter? Of course, I messed that up. And the answer is because it looks like the symbol pi. Really, I think it looks like Stonehenge, personally. It's got to be 18 inches tall. All right. Trying to deselect the pad behind it. Let's turn off some stuff here. If you're new to KiCad, when you're doing a lot of selection stuff here, it's important to have kind of a good feel for like how how to selectively hide things so that when you're trying to do some of this stuff, it doesn't burn you. So like I just turn off the back, um, one there, and I'm just doing that to do this. And then of course I got this one upside down. All right. I don't have key logging turned on. I do apologize about that. So sometimes it's kind of hard to tell what I'm doing. I'll try and talk through it. So what we have here though is we have the UFL connector. What's going on here? That's right. Okay, that's weird. We have the UFL connector here. And this is the feed line for that, kind of like a coax. This coax. And then that's going up out to a connector, which is also going to be 50 ohms. So the connector is 50 ohms, the cabling 50 ohms, the antenna's matched to be 50 ohms. So what you want is something that like looks like 50 ohms all the way back from the pin all the way back and out there. But I'm talking about controlled impedance stuff here. So how does that work? So because I already created some net names, it's down here. I do have to apologize. Some of this stuff has already been done. So I'm going to go and I created some net class assignments now. And so this is probably a better example here. You see that NRF 9151 star. So anything with that I specifically named NRF 9151 and then stuff after it, that I set as 50 ohms, right? And so you see that basically this is setting up a pattern, and then the assignment here, I only have 2 net classes here, but I'm assigning the 50 ohm net class. If I do USB later at 80 ohms, sorry, 90 ohms, I will assign that to be USB 90 or something like that, where basically there's going to be different characteristics there. Now, how do we know what the actual clearance and track width are, right? So those are set here, actually. So this is non-differential, so we're actually not going to worry about DP width, DP gap. Those are differential things here. Micro via size and hole, we're not using those. And then via size and hole, that is not, I plan to keep everything topside, but I think even vias, they are a discontinuity, but you don't, I'm not sure about the sizing of that. So that's put a pin in that for later. So the only thing I really changed here, and really only one thing I changed, was this right here. So why is this 0.2939 and the default track width is 0.2 millimeters? The answer is because I'm following a stack up from JLC PCB I talked about at the beginning. Where is it here? Okay, so let's go through. So I use JLC often. It's not the only one out there. But the thing that you need to know is you need to know the stack up of the board, and then the material type, and then and then you're going to use those things, and then I guess also your kind of your topology of how you're creating these lines, and then you can use that to calculate your line width. Because of physics, the combination of your topology, either strip line or coaxial or all the other ones that are out there, and basically the geometry of how the copper is kind of set up with the dielectric, which is the FR4 fiberglass, not always FR4, but basically the dielectric constant of that material in between the copper layers. That's ultimately what sets it up. So if you've ever cut a coax cable from the cable company in half, usually there's a copper conductor in the middle, and then a bunch of white stuff, which is really dielectric around it, and then a ground sheath running all the way back. That's ultimately what sets up that characteristic impedance. That's how they're able to send the signal so far without losses. Well, there are still some losses, but with minimal losses. And that's kind of what we're doing here. And so I go to controlled impedance, and that's this one here. And from here, I'm setting a couple things. One, I'm setting the thickness of the board. And then, so standard thickness is 1.6. I actually prefer a thinner one for modules, because then you can lower your overall height as well, especially if you're stacking these things on top of one another. Copper weights, outer copper, inner copper, 1 ounce, half ounces are pretty standard, but ultimately these are things that are going into the calculator. Let me show you another calculator here. KiCad. Sorry. This one. So we can go into calculator tools. There we go. And then ultimately transmission lines, this is what I was talking about here. So this is microstrip. This is if you don't have any copper plane around it. So you need to have it without, within a certain, I think, like 3 or 4 trace widths away. You need to make sure there's no ground pour on the top side. I almost always do coplanar waveguide because I like to do a ground pour. And so then ultimately S is the distance between, that's basically the clearance of the trace that we're talking about. And then the width of the trace is what we're going to be setting. That was that 0.2635, whatever it was. And then ultimately these other things, the height of the dielectric, the thickness of the copper, and then the assumption here is that there is a ground plane underneath this layer. And that's really, really important. Sorry, there we go. And that's the assuming there's a ground plane underneath, because it's really all about how the electromagnetic fields are interacting with the other things on the board. In this case, ground, right? So this is ground in the ground plane, ground in the pore that's on either side there. And all of that in conjunction with the dielectric is ultimately what derives your characteristic impedance. I think I've stretched the limits of my physics. So if you want more, there's lots of great videos on the internet, including not so great one by yours truly. I gave it a DEF CON, and I mentioned SuperCon already. All right. So I usually don't even use this. I usually go to something like the vendor that I know that I'm going to use. And then I say, hey, do you have some suggested values for me? That's even easier. And that's ultimately what the screen we were looking at here. So what I chose the thickness of the board. They have a couple options for stack up. I chose this one here, 7628. That's the one of the material types that's in there. Ultimately, cost will be impacted by some of this stuff, but I don't really have a preference. What you might run into is if you had traces that were so wide to get to 50 ohms or so narrow that you weren't able to hit the specs, then they might push you to a different material type because they have different dielectrics, and you could start to draw different line widths that fit your other needs. So there's going to be some back and forth here. I'll tell you right now, I've already done this stuff, and I did figure out that value there. So from here, I chose the stack up, right? So I'm doing the JLC 04081H. So that's basically I think 08 is the height, 081 is the height, 04, I'm not sure if that's the rev. Oh, 4-layer, there we go. JLC, 4-layer, 0.8 millimeter height, and then 7628 is the material type of the prepreg. And you see that there's prepreg here, 7628, and then there's a core, and these are the different thicknesses. And this is just how they slap all this stuff together, all these material types when they're making your board. If you haven't seen it, go watch Scotty from Strange Parts. He has a JLC tour and I think a PCB way tour, but basically seeing how PCBs are made is also useful in this regard. Okay, so we've chosen that. Now I go and choose it here. It's a little bit hard to see it because they have the Chinese characters in addition to it, but I'm just character matching on the JLC 04081H 7628. Basically, if I change this, it actually does change the width of the other things here. Then I type in certain things here, right? Coplanar single-ended, right? I then say signal layers on layer 1. Top ref is not there, I don't think. Yeah, that's right. No top ref because of the type that I'm doing. Bottom ref is layer 2. So basically signals on layer 1, grounds on layer 2. Trace spacing is not relevant because I'm not doing differential. And then impedance trace to copper, this is basically saying what is the clearance around my trace itself. So I set that at 0.2 millimeters. I hit calculate, and then ultimately this 0.2939. Did I get that right? Ooh, let's see if I got that right. 2939, I did, great. So that's what I set there. Now another thing I'm going to do is I'm going to, at manufacturing time, I'm going to put the stack up into KiCad as well, right? So I'm starting from a default stack up here, but you can define your own. And basically, I'm going to match all this stuff to match the JLC one, so that if at some point in the future I decide not to go with JLC or whoever the first board maker is, you want to have that spec sheet basically traveling with your board so that they know, oh, he wants to use 7628. He wants to use this thickness of prepreg, this thickness of core, that sort of thing. And ultimately, that's going to get your best shot at making it the same. Then you can also, in a lot of these board houses, so when I use something like Macrofab, you can also call out and say, hey, this is supposed to be a 50 ohm trace right here. You actually say like, this part of the board, this trace right here is 50 ohms. And in doing so, they'll go and check it for you. They'll do additional simulations. They'll check it. I don't think they guarantee it, but it's like best shot there at making things. Another thing we benefit from is the fact that there is a very short feed line. So if I was running this across an entire PCB, it was very discontinuous, and is that a word? Had a lot of discontinuity at the start and end because it's a different impedance. Then you could start to have some signal loss there, and your little cell thing might not work as well as you thought it would. As you go towards production, if you took something like this to production, you want to confer with a RF expert. You'd want to have an EMC expert as well, so you make sure you're not spewing signal in the wrong realm. And then changing your manufacturing process to match this, and doing testing as well, right? You can use something like a time delay reflectometer, which is basically send a signal down the line, you see how long it takes to come back. That's basically testing the characteristic impedance of a signal. Those are expensive, but ultimately it'll test. That's what board houses do, to test just how good their tolerances are and that sort of thing. All right, we're up to 3 watchers live. Thank you. Okay, let's actually route some of these traces now. So I'm gonna let's first do a trace here. This is actually going nowhere. I guess it's going to the one next to it. But this is set as a default net class right here. You see I have track use net class width. If I hit B, you'll see that it draws a clearance around that trace. This is just set at the default. I can verify that by selecting this, selecting the trace, hitting E, finding the window in my multi-monitor setup, and you can see that it's set at track width is 0.2, and I know that that's not the controlled impedance one because I know it's 0.2939, right? So this one is not that. Now I've also have a predefined size here, 0.127. This is something I did in an earlier video to see if we could get through different regions of the board. And yes, we could. But ultimately, this signal is not, you can even just see from the net name, U9 VDD 3P3, right? So this is the 3V3 line going here, but ultimately this is the one that I assigned a net name to, ESP32C3 feed 50 ohm, right? And so because, I think I have to go back into my net classes, I need to change this. I'm going to make this, nothing matches currently. See if I have the wildcard here, it does show up the LTE and GPS ones that I created, but instead I'm going to make this one a wildcard as well. And now you see, oh, too many things here. Man, okay, well, let's have multiple entries. Int star, and we'll make another entry here. I guess it's good to see this as well. And then we'll do feed star and set that to 50 ohms. Okay, so now when I start routing this trace, both the feed and the antenna net names, it'll be a different width. That's ultimately all we wanted to do, right? So now we have defined stack up from JLC in this case, but it doesn't have to be JLC. Let's try it out. I hit X, start routing. I don't know if you remember, but that actually does look a little bit smaller, or larger rather. So the clearance is the same, but now let's hit B. Okay. Now this might be problematic here because, all right, so this is not actually routed yet, or this is routed, but it's not. What you see here is actually, we don't have any copper on this side of the pad, or on this side of the trace rather. And that is problematic because that'll actually show up as a discontinuity because the kind of the expected signal interaction between the trace itself and the ground layer on either side is not there. So instead, let's go and redraw this. I'm going to draw this out the side now. Oops, one more. So there we go, draw it out the side. Nope. Click to start it. There we go. I don't love that. All right, let's do another little trick here. Let's right click, I'm going to say group. So now this is a group of items. I should be able to then, can I rotate the whole group? Nope. All right, never mind, ungroup. I'm going to do these individually. go to the general, 35. I'm gonna offset it by 45 degrees. Sometimes when you're looking at a board and you're like, why is that a weird orientation there? And sometimes it's because they want to the same kind of thing and have kind of better signal integrity. I'm not sure that's actually the right term, but once you're on a 45-degree angle, you can just rotate this thing to match what you need. Okay, so now should be able to rotate it like this, and like this. Make sure they're not overlapping because it'll bark at us later. Okay, I think we're all right there. I want to move this guy up a little bit. Select only traces, delete those. Not sure what I have turned on here that is only showing the ghost mode. It's definitely one of these things. Full window crosshairs, sketch pads, sketch traces. There we go. I think that's it. Yeah, there we go. Okay, so now it still might not be enough. So we're there, but this is weird because it's like they put this power input right next to the feed line. So maybe they expect it to come out the side. So let's try that, I guess. Make this go a little higher. And so this is it's kind of what I'm talking about with what was I talking about? At the beginning, I was saying I want to leave some additional room. You know, basically what I'm doing right now with this kind of weirdness to try and get these controlled impedance traces going out to the UFL and the feed lines or the antennas, if there's antennas on board, sometimes you just need extra geography, and it can get kind of tough. And I am not the best at this, just so that's clear. So let's see if we do it like this. It looks terrible. I'm just trying to get ground on either, like a best case scenario, ground on either side of this pin. I think that worked. And then this connects here. And then this connects here. And this connects, yeah, here. There we go. All right, now what I'm also going to do, this is completely silly, but it's actually fun, shows a fun thing in KiCad that's a lot easier than it used to be. So if I select these two tracks, right click, and then I say fillet, there should be a fillet somewhere here. Did I do a little trace? Where was it? There we go, fillet. The radius is so incredibly tiny, it's not going to matter. But now it's curved. And you might say, well, why does that corner really matter? And there's a little bit of reflection there. Ultimately, I'm not doing good enough RF that matters, but it's pleasing to my eye at least. Other things I'm going to do here, I'm going to just as a placeholder for later, do things like this, where I have vias so that the ground connection right at the feed is connected to the ground plane that's lower, the lower 4 layers there. And I'll probably do things like this all the way down. That sort of thing, probably overkill, but ultimately I want that to be as low impedance as possible from the top layer ground to the inner layer grounds, which are really the best grounds. And so I'll do that on either side there, so things like this too. And yes, that'll end up biting me later when I have to move all this. If I move this stuff, whenever you start dropping, generic vias here, they start to they mess up your layout later. Okay, so let's see what that looks like on the thing. Let's save. Saving is good. I think saving is a good idea. All right, so that looks hideous. Let's do this. You may notice you don't have a lot of reference designators, especially on things like this. I personally prefer to turn this off. Mike, my coworker, does not prefer that, especially when we're troubleshooting. And he's right on main boards, but I think for modules, I'm going to win today. So I just turn those off. And let's do that here. There they go. And so this is what it kind of looks like. I think those vias are not optimized for the process that we're going to use. So we can get smaller vias and get them closer together and tighter, that sort of thing. But ultimately, this looks like an okay feed line to my eyes. So flows out from the ESP32 out to that center terminal, out to a UFL connector, either UFL to SMA or UFL directly to like a flexible antenna, and away we go. Okay, let's do the same thing up top now. I already know the GPS is wrong, so we'll hold off on that. This one is NRF9151 LTE 50 ohm. I think I named this other one LTE feed. Let's match the naming capability. So we'll do this in the schematic first. I did a like that feed. I did a wildcard, so anything after feed LTE rather should be good. I probably should do the same for the ESP32C3. And these are really long, but aside from like how they display, it's not a big deal. Like, it doesn't matter that they're very, very long. All right, let's go do this because then I have to go. Should have just called this the controlled impedance one. All right, so we hit F8 to make that go. And then let's route this, nice and easy. Route this one, also really nice and easy. Hit B to redraw. And then I'm gonna route this one here. Now you see this one has a nice big bend to it. Also has 2 ground pins on either side. I appreciate that. And pull this up a little bit because that now the feed will be good here. You see a ground. That's awesome. That's exactly what I want there. This should also have the same 2939, which is good. That's our marker for that sort of thing. And then let's select the whole trace. Hit U. Just select the whole trace. Right click. Now we'll actually put in a respectable fillet. Let's try that a little bit. Let's try more. Let's try 3. Going wild here. How's that look? Oh, I only did 1. Well, that's weird. Oh, I might not be able to make this bend. Yeah, so you need a certain, let's see if it gives an error when I do that. Yeah, unable to fill it because of the size. So basically because this line is, the feed is too high here. Let's try that. Select U, right click, fill it. Let's try 3 now. There we go. Look at that, nice and round. Okay, that's great. If you didn't know, these are the USB lines up here. Those are actually going to go on the lower side. And so I don't know why I thought this was going to be the end of layout. Of course it's not. This one, this is the power line. So basically this is what turns the power on and off to the GPS section. And that's a coexistence thing. So this is something that's inside the NRF9151. That allows it to turn off the it basically shares the same preamp between the GPS and the LTE. And that this part here helps with that sort of thing. So I'm pretty sure I named this wrong. Let's see, coexistence GPS enable. So really we just need to have, this is basically feeding power in through a filter as well. Let's go to here. Yeah, so here's the GPS feed. I'm not going to be able to bend that one, that's for sure. I could try and rotate this as well. There's just not a lot of room here, unfortunately. And so I don't really want to move this module down too much. One thing I'll call out, Nordic is wonderful. They'll actually review your whole design. And so if you're a Nordic user, you can send them your design, they'll give you feedback. A lot of the other module manufacturers do the same. I'm not sure, I've done the same with an old crypto board. So crypto will also, on a BG95 board they did some review. That was less on the RF side and more on the, are you following the app note sort of thing? Also super useful. And yeah. All right, let's see if we can do this real quick. What else is this connecting to? So this is just going straight to here. Oh. All right. Interesting. That, I really much in the same way. I don't want to do like right turns here. GPS power. So this is actually just a power line. So that's just going here. That's a capacitor. That's ground. Let's redraw. And these signals are going to also be on the bottom side of the board. It's probably, so here, oh, this is ground, SWDIO, SW clock, and then we get into the optional, some of the optional pins here, and the, that's interesting. This is supposed to be the USB on this side of things. So what we're seeing here, though, this one has been assigned the GPS 50 ohms, but this one, the GPS, has not. And so let's just match that same naming scheme here. So this is GPS int. Copy that. So paste this. Feed. Ooh, that's ugly. There we go. It's off the page, but we'll fix that later. And then we need to copy this to make sure that we're actually getting the right net names here. Okay. Then I need to update the schematic to the layout. Should see the new net name here. There you go, GPS feed. GPS ant. Need to go into the net classes. I need to do, oh, actually, because it's 9151 star, that does work. Great, and those are all good. So now, when I redraw this, it should actually, yeah, that's good. So now, select all that. I should see this is now the right spacing. Good. So not quite the curly swirly that I'd hope for. Let's do this. Let's try one more time. Interesting, this actually will work, even though it's not on the whole pad there. And I'm not sure if that's best practice either, but it's going through the pad so the net has connection. Let's try and fillet this as well. We'll do a 2mm fillet radius. Let's see how this looks. All right. And then we will, interesting. So the ground is not connected through here, so we would either have a gap here. Not sure why that is. I could also potentially, oh, that's why. Because usually this is this side would be connected to ground, and so it'd be on the same net, and so it would just kind of close up that gap there. So that's another thing to look into there. All right, so once again, I've poorly named the stream, poorly timed everything. This is we're at about an hour. You wanted a part 5, right? So I should have called this the RF layout. But we have some more parts coming in here, and I'm hopeful that within, say, 4 more sessions, no, I'm just kidding. I think, once once the parts are in place, once you have your placement kind of set up, then you're in good shape for this sort of thing. So I will double check this with my RF friends, And if you have any thoughts, you can always leave them down below. You can go over on our forum. We don't actually have a section for hardware, but maybe we should have one. Also, let us know somewhere else in the forum if you're interested in that sort of thing. So that's all for now. Thanks for watching. See you next time.